Hello everyone, and welcome back to another cartography lecture video. And in this lecture video, I want to move away from talking about raster data structures and this idea of resampling, which was the generalization technique for rasters, to talk about how we can start to generalize vector data. And vector data behaves very differently because, again, the difference between the data structures, right? Raster data is this regular array of squares, which we can generalize by simply changing the size of the square and then using one of those four approaches to figure out what value to assign the new square. With vector data, right, we're dealing with direct sort of coordinates, right? Points or points connected by lines to form lines or polygons. And we have to come up with a series of approaches to deal with that sort of data structure. Now, what I want to do is I want to cover 10 sort of common, I don't want to call them categories, we'll call them approaches, right? 10 approaches to generalizing vector data. And I want to be clear here that I'm talking about these 10 approaches in an abstract sense because the specific implementation is going to vary depending on what software you're using, what specific data types you're using, as well as the fact that these are just 10 and there are a lot of other nuanced approaches that you might come across in various literature and various mapping softwares. And so my hope is that in this video and possibly in the next video, we're going to cover these 10 approaches. So the first approach has to do with addressing that last concern of generalization, which was that idea of conflict. When you zoom out and your sort of fine scale detail becomes noise, the first way that we can address that is with this idea of simplification. So our first approach is going to be simplification. And the basic premise of simplification is we remove vertices which reduces the complexity. And if this word vertice here, if this is tripping you up a little bit, I want to take a second to just remind everyone that the vector data structure consists of the idea that we have points called nodes or vertices, right? So we could have maybe, let's say, we had 4 points, right, vertices, connected by, let's make that one a little clearer here, right? So this could be a line geometry, right? We have 5 vertices or nodes connected by 4 edges or lines, right? And so you could imagine that this particular instance, right, we can simplify or remove vertices. Right? We could remove, maybe we could remove this vertice and this vertice. Oops. Right. So you can see here we've reduced complexity by removing 2 vertices, but we've kept the same general shape. Right, and that's the key thing with simplification. I'm going to make a note here in red. Right, try to remove vertices that don't disrupt the general shape. All right, and so you can imagine that there's a lot of approaches that you could take Say, for example, you could just remove every other vertice. That's called the nth vertice method. But you can imagine how that could end horribly if you were to remove the wrong vertices, and you could completely change the shape, which could lead to that which could lead to one of the other issues that we have, such as conflict, right? This will address complication, but you have to be careful that you don't introduce conflict by removing a vertice that drastically changes the shape. So that's simplification, right? Another approach that we could take to address this same issue is called smoothing. It's called smoothing. And essentially what smoothing does is, instead of keeping vertices that make angles, we start to introduce curves. Right, smoothing uses curves to replace sharp angles. And this essentially works on the principle that the human eye sees sharp angles as more complex than smooth curves, even if they're showing the same sort of shape and outline. So for example, right, if we were to do the same thing we did before, where we have these sort of points set up, maybe something like this. I've exaggerated it again here. I've exaggerated it slightly, right, that we would have this sharp point, right, that we could turn that into right, instead we could turn that into some sort of a curve. Right, and you can see that even though we've maintained the same shape, by replacing these sharp angles with curves, we've addressed some of that issue of complication or complexity. And by doing this, right, we're far less likely, right, by doing this, we're usually less likely to introduce that conflict where we've changed the geometry such that we've caused geographic issues in another data set. So again, simplification, we remove vertices, trying to do so without changing the shape. With smoothing, we replace sharp angles with sort of smooth curves, and this gives the idea of reduced complexity. So let's talk about a different situation. Let's talk about a situation where we have a bunch of points. Let's say we maybe have, say, 5 points like that, right? And as we change scale, right, we end up with that issue of coalescence or congestion, and we end up with points that look something like, maybe now they're starting to look something like this. Right, we've reduced that map scale. How do we want to address this, right? How do we want to address that issue of coalescence and congestion? Well, what we could do here is we could do what's called aggregation. Right, aggregation. So aggregation would basically take these 5 points and as we zoom out, right, rather than keeping them as points, we can simply lump them together into a polygon. Right, so this is point to polygon. Right, so aggregation sort of put a more specific definition on it. Converts point locations to an aggregate area object. So let's imagine that we have the same issue, right? The same issue, but instead of these being points, right? Let's imagine that these are actually geometries. These are areas. They're polygons, right? And we have the same issue. We zoom out. This was sort of the prototypical example we talked about when we talked about congestion and coalescence. Right? How do we address this issue? Well, with points, right, we aggregated them. We converted a series of points to a single aggregate area. Well, with polygons, we do something similar, and we do what's called amalgamation. Which is called amalgamation. And basically what we do is when we change our scale, right, we fuse these polygons together. Right, we basically pretend that rather than having them be different polygons, they actually are all just one polygon to begin with. Right, we blend these lines together to make one polygon. Right, we group individual polygons into a single polygon. So aggregation works when we do points to polygons. Amalgamation does the same thing when we go from multiple polygons to a single polygon. I'm going to actually stop the video here. We're going to cover the other 6 in the next video. Hopefully this all makes sense. And as always, if you have any questions, please reach out. Thank you.